our physics response. That's great. Right, but you should think about more what data means, what distance means in a data set in general, right? Because it is about how similar these data points are. So if the data set is about people, then how similar those people are based on the data you have, right? So if your age is the same and your income is the same and you live in the same city, your data vector describing you is going to be very similar to someone else. So those qualities are the same, even though you might, be different gender and different other stuff. So it depends how they're described. So, but distance is very subjective too, right? So it's not clear that it's like, oh, they're similar. If the distance is the same, then they're the same. That's definitely not the case, right? Because it depends how the features are represented, right? If it's like I said, where you're talking about census data with information about people, how do you weight them? How important is age, right? Age. Well, this is a good example to talk about normalization, right? So in our slides this week, we had normalization, right? Okay, well, this is the one you want to talk about with kurtosis. Normalization in here too? No. I need a better system for having all my slides available for this kind of session. Types of mean functions. Nope. Or normalization thing too. So hopefully people saw that. Right. Sorry for flicking through slides. Oh, it sucks. Okay. Right, and so when you're normalizing, it's really important because that will change the distance, right? So if we're talking about the distance between two data points, which are humans, based on all their census data, age is a number that ranges between 0 and 110, 113 or something, right? So you could say, set the max age for humans at 115, 120, and the number will be meaningful. But most people, are under 90, and so it kind of biases that data a bit. And if you're talking about distance just between numbers, and say you've got income, and income is not distributed the same way age is, right? Age kind of has a kind of fairly normal curve, and I do mean that in a statistical sense. So there's a Gaussian that is kind of like a peak. Maybe there's a couple peaks in some countries, depending on history. But there's usually some age that has the largest, and it peters off in different directions, and it drops very suddenly, kind of at the end, unfortunately. But income's not like that, right? Income's like this crazy multi-peaked thing that has low incomes and then some middle incomes and very high incomes, and it's different in every country. So if you talk about the distance between a vector that contains age and income, that distance takes into account how important you said each of those was, and even how you normalized it, right? If you normalized it with a max, then you put a bias saying this is how rich anybody can be in this country. Maybe that's as rich as anyone could be in that country historically, but there's always room to grow. And Z-score would handle kind of, as we said in the video, Z-score is usually the one you want to use because it's normalized for this kind of standard, actually Gaussian kind of assumption about most data. If you know your data is definitely not Gaussian, maybe you shouldn't use Z-scores. Maybe income shouldn't be done with Z-score. But most things work pretty well with it. Yeah, so in terms of this, what does distance mean? It really is subjective, and it's something you got to be wary of, right? Because however you normalized it, however you weight it, is going to affect whether these data points are similar. So if you use that to basically decide who should get, money, or who should be, arrested by the police, it's very important to not just assume distances similar is similar. But as a concept, you need to be able to do it. There's many types of distance functions, many types of normalization. You have to have all of them available in your toolbox and figure out how to use them and when to use which. And I can't necessarily tell you when. There's lots of advice, but it depends on what you're doing. But the first status of that is you have to know what they are. So we had a question about kurtosis, and I don't know if I have a good intuition for it. It doesn't come up that much, frankly, in terms of people talking, what I see, but it's a good thing to know. And in the same way that the distance method that you don't usually see a fifth order Minkowski distance saying, oh, what's the 5 with k equals 5, you can define it. And in terms of these summarization central tendency classic methods, obviously you can define it as well, right? Because you just say that there are more. We have it defined, right? So it is defined here, where kurtosis is the fourth moment of it. So skew, mean and median are important, right? So median is our average, so we often use that, and it's not necessarily the best thing. People use average, even though they probably shouldn't. Mode or the median. Oh, I guess they're, yeah, sorry. There are two different ways of looking at that. The most common object or the one that's in the center based on data. They're often more stable than the actual mean, the average, because the average can be thrown off by very far off data. But skew kind of tells you this, whether, in what we talked about, normal Gaussian is the perfect one where the mean and the median and the mode are all equal, but skew and kurtosis are 0, right? So everybody likes Gaussian or normal distributions because they have this nice behavior. You don't have to worry about these guys, and all these ones are equal. And a lot of things in nature behave that way, which is interesting, but not everything for sure. And so skew just means, yeah, it's off in one direction. Kurtosis is like the acceleration of how far it is off in that direction. Is the only way I kind of think about it. Or you could talk about the heaviness of the tail, right? So how much area is filled into this kind of infinite digression into the distance. If it drops off very quickly, then the kurtosis is low. If it's high, then you really have an uncertainty about any value of data, right? And most times it's either one or the other. I don't think it's usually like this middle thing, right? It could be that any data point's possible, but you just don't see them that often, right? So if you're talking about predicting lottery numbers or stocks or something like that, the tail might be very long because it's a very random process. So anything could come up and that tail just keeps going. But if you're talking about age, it might have a kurtosis kind of skewed to one side, but it's really going to drop off and hit 0, right? So the kurtosis on age as a distribution would be very low, is my intuition for it. Okay. Okay, so a bunch of people talking about the lecture and holiday and stuff. So I don't know if I clarified that for everybody. I will make an announcement and post it up here. I did move the virtual classroom event for this for next week already. So it should be on the calendar on Learn. Basically, next week's live session is moved to Thursday rather than Monday. And yes, the live session is a discussion of the previous week's content because otherwise, there's no point in me talking about it if you haven't had a chance to look at it. So there was all the videos and great. We'll do that in moment question as the last thing. You have the slides and the videos available for this week, for last week. And once you've seen them and can digest them, we can kind of talk about it and go through things. If we can try to come up with examples or group work for people to do, that would be great. But if you come with questions, that helps. And I see some private questions that I missed before. Sorry about that, guys. Yeah, that'd be the structure. There are some contents that I don't have up on YouTube videos yet or lectures. So when I have something new, I'll use this slot to do actual lecture and do something new, unless I get time to record it ahead of time. And we'll see how it goes. And if we need more of that, everyone in the same group talking, we can use the Thursday slot as well. Right now, I'm leaving Thursday currently to be just, if you want to book a time with me, you go into Doodle and you do that, and then you can find me, right? So bookable, and you can book 15 minutes or half an hour if you need to talk about something in detail. Yeah, so I've moved them to be this Thursday. Okay. And always there are questions on Piazza. I was going to go through those, but you guys had good questions here, so I'll try to follow up. Or the TAs will look at it. They have been answering, but I'll try to help as well and see if we can answer some more of those. But they're kind of along the same lines we have here, kind of some specific thing from the slides. And okay, so central tendency. What is a moment in central tendency? That sounds very philosophical. Is a moment. It's, how do we define this? I mean, this formula defines moments in central tendency. Basically, I mean, average is a fancy way of saying, generalizations of average, right? Average is average. You add all the numbers, you divide it by n, right? What's the general form of that? You add some formulation of the numbers and then normalize it by something else, but in a higher order, right? So mean in this formula, if you set k to 1, so we can use the discrete version of it here. It might be a little easier to understand. Right, so we've got a continuous version and a discrete version. I hate when it does that. If I don't write fast enough, it starts turning to drag. And so what are we talking about? So we have all the data points x that we currently have. So a normal thing when k equals 1, this just becomes 1. That becomes 1, so you get n minus 1 plus 1, which is just n, right? 1 over n, sum all the values of n, and subtract the k minus 1th moment, right? So the mu1 is average, right? I'll try to write my mu better. Sorry about that. That is embarrassingly bad. Mu1. Mu0 is 0? It's nothing. It's not being used. Did we say that explicitly? It would have to be 0, right? Because we want to disappear, right? And so that would be 0, and this would just be x, and then that'd be n, and this is literally average, right? And so then once k is higher, you're talking about the difference between the data points, the sum of the data points, and the mean, or the previous one, right? So for the variance, you're talking about for every data point, how different is it than the average, right? Compute the average of all the data first, right? Compute the mean, and then for every data point x, figure out the distance between it, right? And that gives you this difference, right? And you add all those differences, and then you normalize it by 1 over, in this case, n minus 2 plus 1, right, which is n minus 1. Why do you have to do that? Because you're comparing points to points, right? So you can't have n points, you have to have one less point because you're comparing pairs of points. And that gives you the variance, right? And the standard deviation is the variance squared, so we kind of use that. But yeah, and the skew is the same thing, but where instead of comparing to the average, you're comparing to the variance, right? And so it's just really like looking at, it's like if you think of calculus, right, and say what's the derivative of a function and the second derivative and the third derivative, these are kind of the same kind of thing, where it's the first and second or the third, where each one builds off the previous one, right? So the first derivative of a function is, its rate of change. And then the second derivative could be seen as the acceleration, so the rate of change, the rate of change. This is like the central moment of the data, and this variance is the central moment of the averages, and the skew is the central moment of the variances. So why is it an approximate equals and not a full equals? I don't remember. That's a good question. Even the continuous one is approximate. We'll have to look that up. I literally don't remember. Okay, we got 3 minutes left, and we have a ranking question. Hopefully that helps with moments. That's all I can say. I don't have more intuition. There's probably a really great video out there by some math person, like theoretical math person, explaining moments and making it crystal clear. If anyone can find that, we will post it up. There is there's some really good explaining math concepts videos to people if you want deeper than that. If there's any questions I haven't answered or gotten through, please post them up onto Piazza. These are great, just general questions, and myself and the TAs can answer, as well as other students can answer. Because there's some people who, this is your first kind of really thinking about data in this way and analysis, and so there's really fundamental things to go through, but a lot of people have opinions and answers on them that you can kind of go through. Conversion, I'm trying to read Amrita's question. I have one question regarding the conversion of ordinal data types to interval data types. How do we decide the rank number? Sorry, I shouldn't do that one. I'm pretty dizzy. Yes. Again, I mean, in a lot of these conversion things, it's going to be the same. It's going to be subjective. It depends. Yeah, because we talked about different types of data. Right, you have kind of categorical and nominal data. You have ordinal data, where the only thing that matters is that they're in the right order. So high, medium, low, or like preferences on a poll. Like the poll, like I asked all of you, 1, 2, 3. The distance between 1 and 3 isn't relevant in that poll. All that was different. Relevant was there was high knowledge, moderate knowledge, and low knowledge about a particular topic. And my ordering, my numerical assignment of those things is 1, 2, 3, didn't imply that, knowing having used a method is twice as good as not knowing about it. Right? It doesn't make any sense. It's just an order. So if you're going to turn it into a numerical thing, you have to come up with something. And the problem is it's going to affect the data, right? So it has to be done in consideration of everything else. So the same way where you have to normalize age and income and things like that, it's definitely going to affect the data. There's no such thing as unbiased model or unbiased kind of pre-processing. People like using we talked about uniform distribution versus Gaussian, and some people in classical statistics don't like, Bayesian methods of analysis because they all have to always have kind of prior distribution. Say, well, we assume this is Gaussian and IED, and then we're going to learn this thing. They say, well, you should do something with no priors, with no biases. So just do a uniform distribution over the entire universe of possible things, and then compute the probability by something. And uniform is its own bias, right? Uniform distribution says, I am stating that all things are equally likely. And if you know that's not true, then it's a bias you're putting on the data, right? So in the same way here, you're saying ordinal, like these things have an order, but they don't have any magnitude, but I need to give them a number because my algorithm requires numbers. You are affecting the data, right? So if you make it a scale from 0 to 1, and then they're just fractions in that, and they're evenly spread out, it's probably fine, but it does mean that you are saying the gap between them is equal, right? So maybe they're not equal. Maybe you have a 5-level scale of order, and the order is like something about risk of getting a disease, or number of relatives or ancestors who had a certain disease, right? How many grandparents had, this genetic problem, right? That's not a good example because their more might be better, might be important, right? But you have one where the scale might matter, but you don't know what it is, and it's definitely not, equally spaced. So I don't know. It depends on what data you're using. So, but you have to come up with some number often. The same thing for binary, right? That we or for nominal, right? So nominal, you have like a bunch of labels, like jobs of people. I did not mean to cross that out. And you have to give them a number because you're going to try to organize amongst them. And some algorithm, like neural networks require basically a bunch of numbers coming in, and then you give some numbers out, and everything gets transformed into words and images and other things. But how do you turn, a feature that says engineer, teacher, dentist, bus driver into a number, right? The way we usually talk about doing it is turning it into binary. I have one hot encoding. Okay. Somewhere did one of my videos have anything saying one hot encoding? I think it might be a concept I talk about but never had in a slide. I'll look and create something if I don't. So this is an important thing to look up. That other problem of turning nominal features into numbers is that you take each of these and say, okay, there's engineer, basically true or false, and it can be 0 or 1. Teacher, and these would each be a feature, and their range would be 0 and 1. Right. And that's basically saying a one-hot encoding. So now you've created a whole bunch of new dimensions. Each of them is binary, but now they're independent, right? You can say, well, technically you could be a bus driver and a dentist. But I definitely don't want to say that dentist is somehow higher or lower than bus driver. It's just another value of this thing, right? And if we're trying to do a category, a classifier that takes into account all these things, you have to turn them into a number somehow. How do you do that? So one-hot encoding is in a way, kind of the only way to do it. You can try other things, but it's not satisfying because it does create a lot more dimensions. And it doesn't handle other problems like, well, what if it can only be one of these, but it has to be one and they have no ordering? Now you've got to kind of put a rule saying only one of them can be one at a time, which is a little bit breaks the whole independent features assumption. So it's not perfect, but there's lots of problems like this. Okay, so I'm going to wrap up there. Okay, yeah, so thanks, Parveen. And I did see people's other messages about that hard to understand concepts. So if there's things specifically you can kind of give us focused details about, what would help. There are resources online. Maybe that's something we should try to do more this term, try to find a better list of starter blogs and things. But there's a good way for actually classmates can probably help with this because this changes so quickly. There's so many resources online for understanding a lot of these concepts. And some people come up with really good visualizations and tools. So if anyone has found useful demos or blogs or videos explaining some of these concepts and they want to share it, that's a great thing to do on Piazza. Maybe we could even create a thread for that or a label because it's constantly changing. People come up with the right way to explain it, right? I guess what I'm doing is kind of listing out the things that are core to learn, giving you an initial way to describe it from my point of view. but someone else's description might be better for the way you learn. So we should try to find some more, but let's all help each other do that as well. Okay, so I'm going to wrap up there because that's our hour and a half. And if we didn't get to your question, sorry, try to put it up on Piazza and we'll answer it. And then this week, there's a bunch more videos now on basic classification, supervised learning, and probabilities. So take a look at those videos. And before we talk next, there will be an assignment out in a calendar. I will find a way to export what I have. Okay, thanks everybody, and see you next time.